sitting over there? Oh, that's the guy. Hey. Oh wait, Joni.
What?
Did you do your burger?
No.
I need to get Jim's lunch.
Sure. I feel like, oh.
Just harass the shit out of him.
Yeah.
I want to
Put your
G question mark,
teacher.
but I was going to just put mine there.
Oh, the other person in my group chat is Monica.
Yeah.
Wait, you said that you don't have it.
Yeah, I
I was in design. John?
Yeah, he put his name. He also put it under a home fact.
What is wrong with this kid? Jim Slow. Do I already have a contact for Jim Slow? Should have phone number. 914-486-9.
Who the fuck is
Have you
playing
started
music?
your project for me?
I finished, but I want to do another one.
We don't have 9 minutes.
Why would you do that to yourself, though? I don't get it.
What? Do another one?
Yeah.
It's like, I love it. It's fun.
Okay. I think
Say binder.
I'm actually streaming right now. Binder, but like I give zero shits.
Binder.
Yeah.
You and I should get together one day. Download TensorFlow.
Oh, I don't fucking know how to do it.
Neither do I, but we should figure it out.
I also don't like, what was it?
You're not allowed
I don't like the idea of setting up a Python workspace because it's always, like, I always fuck it up. I'm so bad at Python. Yeah, but like, I still fuck it up. I mean, like, if you want to, I'm down, maybe. It's not a hard no. It's a soft yes.
Alright.
There you go.
I just want to have TensorFlow.
I mean, that would be nice for me as well. Even though on Mac it doesn't work as well. So like, whatever.
On Mac? Oh, yeah.
You can't use GPU.
Do you have a GPU? In your Mac?
Yeah, they all have GPU. But yeah, this hasn't been either.
Which one?
Like a crappy one. But it's still like, it's still better than like using the CPU.
Plugin called CUDA or CUDA. No fucking idea how to do it. But I can use some of
I got that on my PC at home, which takes fucking like, it took a whole day to turn on.
You should, that I'm gonna ask if you can help me out with, because I have no idea.
I think I just like looked it up.
Yeah, I couldn't decipher it.
Okay. If you want, I can work with one. What am I doing? Live streaming. My viewers are happy.
How many viewers do you have? Zero.
But they're happy.
Some guy named Mr.
Wow, it's very laggy.
I'd be happy.
How old is that?
Really? I can see it.
Is this streaming? Oh,
Yeah.
nobody's
Yeah.
watching.
I mean, it gets saved as a video.
Yeah.
But do you trust?
Now he's really.
He's kind of like forgets what he's talking about. Like occasionally, but it'll be like
Oh my god.
What makes it
otherwise.
I don't know, Google it. What the fuck?
What did you say?
He asked what makes a guy attractive.
What makes a girl attractive?
Eyes, general figure, smile, big
Is that like definitive or only for you?
face too.
Okay, but that didn't answer my question.
Those are like the four, basically.
Definitively or just for you?
Pretty definitive. That's about as broad as I can go.
Okay.
What's the truth, Matt? You can at least text me like, hey,
Evan, is anyone sitting here?
No.
I didn't need to have that.
So be careful because there's a wire.
Not gonna start until you're ready, buddy. I was just like, wait for you. Well, obviously the prices are ready. Notebook, anything that's suggested.
Oh, you're talking to me already.
Honestly, I'm just
That's fine. Just watch. I'm sorry. Okay. Oh, that actually works. I'm very clear. Oh, wait, do you want to, like, is it going down the bottom? You can put it on top of your... I'm so sorry. I mean, it is. I just don't... But, like, it's not what you feel. But, like, thank you for, like, not ruining it.
Who's watching?
Oh, is it you?
No, it's not me.
Ah, you have a viewer.
They're not happy. They won't be happy.
No, they're happy.
They won't be happy for very long.
I wasn't even aware you could change it.
You can change the title.
Happiness.
I can't change it. Also, I haven't noticed it before. It's probably a new thing.
All right, guys, we're gonna get started.
But like, can you tell who's viewing?
No.
I hope everybody had a nice Thanksgiving break. Ready to get back into it. Here's our just a little logistical rundown. Everything is the exact same as last time. Exam 2. Rooms are exactly the same. Time is exactly the same. Format's exactly the same. One thing Dr. Meisner wanted me to point out, please, 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 know your ID number, bubble in your ID number correctly.
Write the right one down.
Write it down, and then take the 30 seconds to bubble it in correctly. 45 of you screwed that up on the last test.
40?
She's considering a 10-point penalty if you do it wrong.
How about 10 points extra?
So just make sure you do it right. We won't have that problem.
That's pretty dumb way to lose 10 points.
Like a 2-point bonus.
Yeah, like, I'm fine with that.
Just don't fill it
Make
in
sure you
wrong.
bring your pen. Make sure you
It's
bring
like the
exam
SAT.
tip.
Make
Make sure you bring a number 2 pencil.
You guys ever heard of the,
and a pen and a scientific
Breyer's
calculator.
curve?
Make sure you have extra batteries.
Not like,
The cover sheet is on Canvas. It's been on Canvas for about 5 days. Check it. You have the table of electronegativities, your periodic table, all the bond lengths, and
multiply by
some
10 and take the
equations.
square root.
So just make sure you know what you have before you go into it tomorrow. Yes, the next bullet. We think exam 3 is easier than exam 2. Take a deep breath. This is a thermal. It is, we think it's easier. Any questions? I'll be around after the review. Karchi's got to run. I'll stick around for 5, 10, 15 minutes. And unlike last night, which I've heard,
It's not a 3-hour review.
this is not a 3-hour review.
No shot.
We'll be here. I'm cutting myself off at 10:30. If I go over by 1 second, somebody scream at me.
Take the square root and multiply by 10.
With further ado, here we go.
All right. So I know a lot of you guys struggle with the lattice energy problem, so I'm going to do that one first. Get it out of the way nice and early while you guys are ready to pay attention. So this is a problem from the last year's exam. This is the only lattice energy problem that you put on it. But this is word for word what you're given for the problem. They want you to determine the lattice energy for this compound rubidium chloride, given all of these things. So a little bit of a basic review of lattice energy. It's not that hard. The lattice energy is just a definition of taking a gaseous ion of one thing, gaseous ion of the other thing, put them together, make the solid salt. So the lattice energy, along with the ionization energy for the metal, the vaporization for the metal, the bond association for the nonmetal, and the electron affinity for the nonmetal, all of those energies, the sum of them, is equal to the total enthalpy for the reaction. So, by knowing this, we could say delta H for the reaction is equal to the sum of all those things I just said. So lattice energy plus ionization energy plus the sublimation, electron affinity, and bond association. So now we're given 5 of the 6, which means that you can solve for the one that you don't know. In this case, it's the lattice energy. So you end up having the delta H for the reaction total minus these 4 things is equal to the lattice energy. Now we go to the givens. So we have the fact that solid metal rubidium turns into a gas and has this energy associated with it. The key to the lattice energy problems is making sure that everything checks out using Hess's law. So we're going to write these 5 things down, including the lattice energy, and they need to add up to the enthalpy change in the end, because that's the definition up top, right? So if we have delta H for rubidium solid going to rubidium gas, we're going to write it down. Now, the next key to succeeding with this problem is being able to recognize what equations come from all of these things that you're given. So you have to translate these things, which are given to you in words, into chemical equations that you can use with Hess's law. So first ionization energy for rubidium, what does that mean? It's the amount of energy that's associated when rubidium loses an electron to become a cation. So we have rubidium. And it's also the ionization energy, it's always in the gaseous state. So rubidium, as a gas, is going to lose an electron to form an ion and an electron. So first ionization energy, translated to this equation, the delta H is the same as it was given. Now we move to the next one, the bond association for chlorine. That just means that it takes this much energy to break this diatomic chlorine molecule, which is 2 chlorine atoms bound together, into 2 chlorine atoms. So we have chlorine, diatomic as a gas, getting split up into 2 chlorine atoms. And that has delta H of 226. Electron affinity for chlorine, it just means that chlorine's gaining an electron, and this much energy is released when that happens. So, chlorine, the atom, plus an electron, gives you chlorine, the ion. Now the last step, the lattice energy has to go in there, but you don't know the delta H for the lattice energy. But you know that lattice energy is when you have the gaseous ions coming together to form the solid salt. So gaseous ions, chloride, plus rubidium, yielding rubidium chloride. And this is what we're solving for. Now the reason we use Hess's law is so that we can check all of these things out to make sure that the sum of all of these energies is going to give us back the original enthalpy. That we know the delta H because they gave it to us in the beginning. So all this is saying is that if all of these things are balanced, all of these delta H's together will add up to negative 431. Now, they say that the change in enthalpy for the formation of rubidium chloride is negative 431. That's the molar enthalpy for rubidium chloride. So that means that it's for 1 mole of rubidium chloride. So simplify your chemical equation so that you have 1 mole of rubidium chloride on the right. Similarly, the bond association for chlorine, you're going to have to change that too. Because if you try to do this and try to see if everything's going to cancel out and give you this enthalpy formation at the end, you're going to find that you're going to have an extra Cl2. So that means we have to take this and multiply it by a half. Because we want to have a half as the coefficient for Cl2 in the end. So remember Hess's law? what you do to the equation, you also do to the enthalpy. So now if we want to check all this out, I'm just going to rewrite these coefficients. And then we'll cut this in half, right? Because we multiply it by half. What it is. Now we look and we see rubidium solid on the left. That's what we need in the bottom. 1/2 Cl2. We need that on the left. We're good there. Now we need to make sure everything else cancels out on the left. Rubidium gas on the left here. Rubidium gas on the right here. They cancel out. Rubidium gaseous ion on the right. Rubidium gaseous ion on the right. Cancel. Chloride, chloride, Cl gas, electron, electron, and you're left with RbCl solid on the right side. So the Hess's law works out. You got back to here, which means that your numbers are going to work out. If you get to a stage or a point in this problem where it's not adding up with Hess's law, that means you made a mistake somewhere. I recommend going back and starting it over, because you always get lost in it if you're just going to try to correct it. So now, using the fact that we know that the enthalpy for the whole reaction is equal to the sum of those 5 things in Hess's law, we can solve for the lattice energy, which we don't know. And someone has a lot of swag apparently. So that equation at the top, I'm just going to rearrange it and put the 4 things that are boxed off on the left side so that we have lattice energy by itself. So now we just have to, what's up? What? This one?
Thank you very much.
I love that 122 chair. Are you going to need 22? Well, you're not in sexy head. I can't wait.
So now we're given all of these things on the right side, plug them in, solve for the lattice energy. Make sure you plug in negatives where they are. So if you have to manipulate the Hess's law equations and have to flip one of them, remember to apply the negative to the delta H, or else it's going to throw your numbers off. So delta H reaction was -431 minus the sum of the rest. And that, when you sum it up, is going to be equal to -695 kilojoules per mole. And you bubble that one in on the test and you get it right. Now, do I have any questions for lattice energy? Anything about lattice energy?
How does it make sense that it's negative?
Negative?
Yeah, why is it negative?
That just means that when this salt forms from the gaseous from the ions, that there's a negative, there's a release of energy. That's all it's saying.
Lattice energy is pretty much always negative.
I don't think so. No. Assume that you're not going to be given that. For now, assume that you're not given it because she might want to. Are we good on lattice energy? Good. The next one we'll do is calculating delta H using the bond energies. So with this problem, I've noticed that a lot of people like to try to sum up the number of bonds of each type. I've noticed that people like to sum up the bonds of each type, but what usually happens is everybody misses the stoichiometric ratios. Like there's 2 H2O here, and people usually forget it when they're doing it that way. So I'm going to show you the right way to do it. This is also going to review Lewis structures. You're going to have to know how to draw Lewis structures to do one of these because you need to know what kinds of bonds are in each of the compounds. So they give us this table of bond energies. You're going to have that table in the cover sheet. And they want you to find delta H for the following reaction. Hydrogen peroxide, the methanol gives you formaldehyde and water. You don't have to know how to name these things, you just have to know how to draw them. So first, we're going to start by drawing every Lewis structure. So I'm going to replace these chemical formulas in the equation with the respective Lewis structure. Can everyone see the Lewis structures? Is it big enough? So step one, draw out all the Lewis structures. I recommend putting them in brackets and then leaving the coefficients outside so that you don't forget them in the calculation. Are they given the bond energy formula?
They're given, yes. You're given bond energy formula and you'll have a table of bonds on the formula.
Yeah. So since we're using the bond energies to calculate the delta H, you want to take the difference between the bonds that are broken and the bonds that are formed. Because these two compounds are going to react and break all their bonds, and then these bonds are going to reform on the right. So the difference in that energy is either going to be released or absorbed, and that's how you're going to get your delta H. So the formula is the sum, where's my eraser? Sum of the bonds broken minus the sum of the bonds formed. So we look at each compound individually now. So don't worry about trying to sum up all of the types of bonds from both of them on the left side and then on the right side. Focus on each compound individually. It's a lot easier to follow, and you're not really going to mess up as much if you do it that way. So we have an HO and an HO. So two of them in that compound. HO is 463. And then we also have an O to O single bond, so we'll add that as well. Now we want to add all the bonds from this. So we have C to H, single bond 3 times. C to H has a value of 413. We also have a C to O and an O to H. So C to O is 358. And then O to H, 463. So that's the total energy from all the bonds that are broken on the reactant side. Now we want to subtract the energy from the bonds that are reformed on the product side. So now we go up to formaldehyde. C to H, there's 2 of them, plus C to O double bond. The double and single bond makes a difference. Make sure you don't pick the wrong one on the table. So that's 745. Now, with water, we have a stoichiometric coefficient of 2, which means you have to multiply the total energy from all the bonds by 2. Got to keep the stoich. And with that, we just have 2 OH bonds. Now, if you plug all these in the calculator the right way, you should end up with negative 291 kilojoules per mole. And you're done so. Now, are there any questions on what I did, how I did it, why I did it? We're good on bond, or calculating enthalpy for bond energies?
What? Did you have a question?
It's all right.
Are you guys going to explicitly go over Lewis structures and polarity or not?
That is the entirety of my section.
What are you doing over here?
Lewis structures and polarity.
I was wondering, like, why is it initial minus final instead of final minus initial?
I don't know, but I did initial minus,
You haven't
or I
got
did
the
final
sign-in
minus
sheet?
initial, and I got the wrong
I'll
sign.
come around and give it
So
to you.
initial minus final.
And you had one here. You all take this.
Oh, maybe because, like, the breaking of the bonds, you're going to get.
So those two are probably going to be the hardest two lines
Absorb
problems
energy
on
and
the
break
exam,
down,
so if
release
you're
energy.
comfortable with them, then you should be pretty good.
The way I remember it is like ice.
It's just kilojoules, but I wrote per mole because of conventionality. It's really just kilojoules. It's only kilojoules per mole if it was for 1 mole of, like, if they asked for 1 mole of one of the compounds in there, but they just want it for the reaction, so just put it in kilojoules. There's multiple choice, as long as you have the right number.
Oh, why is it, like, initial minus final instead of final minus initial?
Can you speak up a little bit?
Why is it initial minus final instead of final minus initial?
So we got a good question. Why is it initial minus final instead of final minus initial? And that's because when this reaction actually happens, all the bonds from the reactant side get broken. So all that energy is released and it's all free. Then when the bonds reform for the products, some of that energy gets taken and then stored in the bond. And if you have a deficit of energy, that means that it absorbs more energy from the environment around, endothermic. If you end up with some energy left over, it gets released, exothermic. So since we got negative 291, this is an exothermic reaction.
What did you? G.
The rest of the problems aren't nearly as number intensive, which is good. So the next problem is consider the values shown below for the enthalpies for the phase changes in water, blah, blah, blah.
Someone sent me this on an airdrop. I'm shook.
That's a wow. I feel kind of sad.
I feel sad that somebody sent this to me. Who's M? Who's M's iPhone?
This is why I have a Samsung.
I'm gonna pass on that. I'm gonna pass on receiving somewhere.
It's like
Don't.
it's like my arm.
Oh my god, do not. I feel disgusted. Yeah, definitely. Oh my god.
Another one?
But this is a cute puppy.
Aww.
So it's okay.
So
I'm gonna
they
say no.
give you a couple different numbers
But
with this one,
I
and they're
appreciate it.
asking you which one is most likely to be the delta H condensation for water. So you might be thinking like there's like a dead end, how are you supposed to know this? But it comes down to knowing the energy that goes between the state changes. So they give you these 4 numbers and none of the above, which the choice is never none of the above, unless you have like surge for EM. But you have these values and you have to pick which one is most likely the best choice for the delta H condensation for water. So delta H condensation, all that means to go from gas to liquid. That's to lose energy, right? So then we could strike out the 2 positive options here. So now it's a matter of choosing 6,000 or 40,000. You know that it probably takes a lot more energy to get something from liquid to gas than it does to get it from solid to liquid. Because the gas molecules have a lot more energy than the solid molecules, a lot more energy than the liquid molecules. So if you know that this has to be exothermic, has to lose energy for it to go from gas to liquid, and you know that state change from gas to liquid has more energy associated with it than there is liquid to solid, then you're going to choose the bigger value, bigger negative value. So that's just the logic behind why to choose this one. If they give you a problem where they want to find delta H and they don't give you anything else, it's conceptual. Think about whether it's exothermic or endothermic, the reaction they're asking you about. Even if it's just a state change, it can be exothermic or endothermic. And think about the amount of energy associated between the state changes. So there's more energy associated with gas to liquid than there is from liquid to solid. We good?
How were your balls finding?
Any questions?
It's not that game. It's a different game. What is it? It's called One Reverse.
So it's a clone of balls.
Yeah, I guess. New and improved. Oh my god.
What is this?
I don't even know. It's like an alien.
Alien with sunglasses?
So the next question, they're giving you a compound, OF2, and they want to know the electron geometry for it. So to figure out the electron groups. So an electron group is either a bonding pair or a non-bonding pair. They're each one group. So with this, we have electron group with this bond, electron group with this bond, one with this lone pair, one with this lone pair. So this is going to have a tetrahedral electron geometry. But the molecular geometry will be bent, kind of like water, with the two lone pairs, because they're going to force the atoms to be like downward. They're going to force them down, so it's not straight.
So why would the lone pair not be on the top and the bottom?
It's more like this. And then that's rotated a little bit to the left.
It's different.
I drew it straight, but that's it. Yeah. So are we good? Difference between electron geometry and molecular geometry. Make sure you read which one they're asking for in the
Gas to
problem.
liquid to releasing energy. So
Are there any questions on it?
And then it just takes a lot to get from gas to liquid and liquid to gas. So
Archie,
Yeah.
what was the answer?
Tetrahedral.
that was a pretty good shot, if I do say so myself.
I have to get this one right.
What's it, 10.1 table? So the electron geometries are really simple. They just go down with the electron groups. So if there's 2 electron groups, linear. If there's 3, it's trigonal. If there's 4, tetrahedral. 5, trigonal bipyramidal. 6, octahedral. That's all the electron groups.
See this.
Those are for the molecular geometries. You need to know both, the electron and the molecular. The electron ones are very simple. You just add an electron group. So if it has 2 electron groups, linear, because it can only go in 2 directions, right? If it has 3 electron groups, it's trigonal. 4 electron groups, tetrahedral. 5, trigonal bipyramidal. 6, octahedral. Because that's what it has to do to spread out atoms. The bond energies are all given to you. I don't think so. I mean, I would just be familiar with them. You should know the water one, in case they ask that. But other than that, I don't think she's asking you to memorize bond angle. And even then, you can figure it out.
You should know that as you add more lone pair electrons, the bond angles get smaller. That you should know. As you add more lone pair electrons, bond angle gets smaller. Because that's what VSEPR stands for, valence shell electron pair repulsion theory. So as you add more lone pairs, it becomes instead of.
So the next one, we got a hybridization question. They give you this compound, iodine trifluoride, and they want you to tell them what the hybridization is. The best way to figure out the hybridization, draw out the Lewis structure. If there's one thing that's the theme for this test, is know the Lewis structures, be able to draw out the Lewis structures. Because that'll help you on almost every problem on this test. So, we have I by itself, so that's going to be the central atom. with 3 fluorides around it. Want to look at the total valence electrons. Iodine has 7, fluoride has 7, so the total is 28. So now we got to distribute them. Put a bond, bond, bond. They use 6 of them. Fill the octets with fluorines. Count them up. This fulfills the octet. This fulfills the octet. This fulfills the octet. This one's not quite there yet. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 electrons. 24 with the other bond. So we have 24 electrons. The octets on the fluorides are already filled up. So now we need to put 4 more electrons onto this in some way, shape, or form. So you can't get 4 electrons on the iodine without it having an expanded octet. So that's what's going to indicate to you that there's an expanded octet here. Because we need 4 more electrons on this, and this needs to fulfill some kind of octet, but it turns out it's an exception, and it has the 2 lone pairs here and here. So iodine has the expanded octet. There are 5 electron groups, right? There's 2 lone pairs and 3 bonding pairs. And that's what's going to tell you the hybridization. So 2 electron groups, sp. 3 electron groups, sp2. 3 electron groups, sp3. Or 4 electron groups, sorry. 5, sp3d, 6, sp3d2. So the s is an orbital, the p's are each an orbital, and the d's are each an orbital. In order for there to be an electron group in each of these positions, there needs to be an orbital. So you know there has to be 5 orbitals, which means it has to be sp3d. Any questions on hybridization?
Was I in your phone? How many people?
I don't think so. I don't think they're going to ask you what the hybridization is that.
How do you have 1,207?
They're quick.
Oh, V was
So one of the questions on there, they give you a couple different compounds, and they want you to identify the one that's non-polar. So if the molecule itself is non-polar, that means that there has to be some kind of difference with a partial negative charge and a partial positive charge. So the best way to look at it, draw out the Lewis structure. So we'll start with the first one. We'll draw out the Lewis structure. We have carbon's the central atom. We have a fluorine with 3 chlorines. So if we look at this Lewis structure, you can see it has a tetrahedral structure, but chlorine and fluorine both have different electronegativity values. Fluorine has an electronegativity value of 4, fluorine has 3.5. So that means that this fluorine atom is going to share these electrons with the carbon a little bit more than the carbon's going to share with the chlorines. So this bond is a little bit more polar than these bonds. So since it has an uneven polarity in the molecular geometry, that means that the molecule itself is polar. Are we good on that one? Ammonia, NH3. What's up?
Are they going to give us an electronegativity chart or no?
Yes. Yeah. You get the electronegativity table. I wouldn't expect you to memorize this. Ammonia, NH3. You probably drew this Lewis structure 100 times. The lone pair on top of the ammonia gives you the difference in the partial charges. So that's polar. Water you should just know is polar. at this point in the game because of the electron pairs. So that's out, that's out, that's out. We'll look at HF, hydrofluoric acid. What's the bond? What's the polarity of the bond between hydrogen and fluorine? Fluorine is a 4, hydrogen's 2.1.
Polar.
Polar. So 2 atoms bound together by a polar bond, it's going to be a polar atom. Only one left is CS2. If you look at the structure for CS2, you're going to notice that it looks a lot like CO2, because the sulfur and the oxygen are in the same group. Carbon central atom, double bound to 2 of the sulfurs. Almost looks identical to CO2. But you look at the structure for the molecule, it's symmetrical. There's no difference between the bonds, so there's not really a difference between the electronegativities. So you know that it's nonpolar. Any questions? So one of the other questions, they give you these 5 compounds, and they want you to identify the one that follows the octet rule. So remember, the octet rule means that each atom has to share or own 8 electrons. There's exceptions to the octet rule, like the expanded octets and like the duet rule with helium and hydrogen. They want you to pick the one of these that is following the octet rule. So we'll start with SF6, sulfur with 6 fluorines around it. There's no possible way that that's going to have 8 electrons if it has 6 atoms around it, because there has to be a bonding pair. You know that that has the expanded octet, so that's not the answer. Same logic applies to PCl5. If there's 5 atoms around the central, that one's not going to follow the octet rule, because that's going to have or share in 10. BH3, if you draw it out, boron has 3 valence electrons, hydrogen each has 1. Draw the Lewis structure out. Yeah. Boron is another one of those exceptions. It's a weird one. Most of the time it'll have 6 instead of 8, 12, or 10. So that's not the answer. NO2, nitrogen has 5, oxygen has 6 each. So that's a total of 17 valence electrons. Right there, trying to distribute 17 valence electrons to something that's only bound to 2 atoms. You could try it however many ways you want to. You're never going to be able to do it. So that's a red flag. That's going to let you know that it can't follow the octet rule. So that leaves you with ozone, O3. Draw out the Lewis structure to make sure it's good. This compound also exhibits resonance. You notice you can put the double bond on the left side or on the right side. That's also something you have to be aware of for this test. But this is the one that follows the octet rule, because you can distribute the electrons and actually have them all have or share any. Question? The NO2, there ends up being like a free radical, which you're never going to have to know. It's like, so it doesn't actually follow the octet rule, because uneven number of valence electrons, there's no way you're going to be able to distribute them in a bunch of pairs. Any other questions on this? Any other questions?
Oh, no,
Don't see you in the back.
Now speak up.
I can't hear you, Sean.
Oxygen has how many valence electrons? 6?
Boron is one of those weird ones that's an exception to the octet rule.
That's good.
Because it has 3 valence electrons. What's up?
What's up?
Question in the back? You're just saying hi? It's fine.
Okay, so one of them isn't going to be quite on this level.
So, last problem written down for the night.
Yeah. No.
I'm sure you guys remember this one from the workshops.
However you understand the question. As long as you can.
They want you to draw the structure for sulfite, SO3 -2. You already know that if you have the sulfur with the 3 oxygens around, probably going to have the resonance because you're going to have to put a double bond in somewhere.
Yeah.
Basically, anytime you have a situation where you could put the double bond in a couple different places, that means that the compound's going to exhibit resonance. So we'll start by drawing the central atom, the oxygens around it. I like to start with a single bond in each. Sulfur doesn't have the octet yet. I'm going to throw a double bond here. Fill in the other electrons. Now, let's look at the total number of valence electrons. Make sure we have enough on the Lewis structure. Sulfur has 6, oxygen has 6. It's a total of 24. But since it is a -2 charge, you have to add 2 electrons. So there's a total of 26 valence. So let's count up the ones on our structure. The octets are all fulfilled. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All right, that's not right. These should be not here. Because there's a double bond for this oxygen, which means it needs 2 lone pairs to have 8. Single bond means it needs 3 lone pairs. And you have the extra 2 electrons at the end, and they end up going in the sulfur as an expanded octet. Sulfur is going to be the one most of the expanded octet questions are probably on. Do we have any questions on this? As far as, what's up? It's possible that they want you to pick the resonance structure, yeah, but they're not going to give you one that's like super long.
The most popular question will be how many resonance structures?
Yeah.
Not draw them, but how many?
So you're going to have to draw them to answer the question, but they'll ask you how many. Guys, can you quiet down, please?
How do we do the favorite resonance structure?
So the formal charge on each atom, you have to take that. Is it it's valence total minus. He's gonna do it in a second. The formal charge.
We'll go over formal charge in a minute.
But he's also going to go over the formal charge. You have to pick which resonance structure is the best using the formal charges. That's basically pick the one with the lowest formal charges on it and the lowest total, because that's usually the most stable.
All right, I'm going to go through some of the more conceptuals just like last time. Again, these are just like the last review where they're more participation based. These are just some basic thinking questions, and then I'll leave one more time. And I just want you guys, we're just going to go through a little bit of each section on the test, and we'll start here. So question 1, which element has the smallest atomic radius? Carbon, silicon, beryllium, or fluorine? This is on campus already. This is that PowerPoint Dr. Meisner posted yesterday. It's under exam. I heard fluorine. Why?
Okay.
Top right. Remember, atomic radius increases to the left and down.
There it is.
Right?
Francium
As we go towards the one element, atomic radius increases.
most
And as we go down the periodic table, atomic radius increases. Very good.
I gotta go,
Fluorine
guys.
is the most electronegative.
Question 2. Arrange these 3 atoms in order of increasing radius. Xenon, iodine minus, and cesium plus. What's up?
Wow, my roommate is actually watching your stream. I don't know how he found
Anions
your
are always
channel.
larger, right? Cations are always smaller. What?
Ryan BC.
What's up, Esteban?
There's a chemistry. No, just
Remember, cations are smaller than their atoms. Remember, cations are smaller than the atoms. Anions are larger than the atoms. All right. So it would be cesium, then xenon, then iodine. Any questions there? Remember that popular question from Dr. Meisner, she'll give you 2 sets of 2 and ask you which ones are right. So maybe sometimes you'll have just 2 atoms, and then the other pair would be an atom and an ion. Anions are always larger because of the addition of the electron. Cations are always smaller because of the taking away of electron. Up. So we have these 5 ionization energies. Ionization energy 1 is 786. Ionization 2 is 1580. 3 is 3230. 4 is 4360. And 5 is 16,100. Which of those elements up there could it be for the, could possibly describe those ionization energies?
Go to the periodic table.
That doesn't help me. I can't hear anything. Silicon. Why is it silicon?
The 4th one is
4 valence electrons. So remember, ionization energy is the taking away of electrons. So if you look at the periodic table, you're going to move back 1 space for every ionization energy. When you get to a noble gas configuration, that is the most stable place that an atom or an ion can be. So to pull an extra electron from a noble gas configuration is going to take significantly more energy than all the ionization energies before it. So the way to do this question is to look at where the jump is. So in this case, the jump is between the 4th and the 5th ionization energy, which means after 4 ionization energies, this atom is stable. So which one of these 3rd period elements has 4 valence electrons? Silicon. Does that make sense? You said no. So that's for silicon, yeah. Nice. This one is definitely showing up tomorrow. For which element is the gaining of electron most exothermic? It's a tough one.
those strawberries are more general purpose.
This is electron affinity. All electron affinities are exothermic. Zaman. What's up? Yes. Remember, electron affinity is the exact opposite of ionization energy. Whereas in ionization energy, we're trying to take away electrons. Electron affinity, we're adding electrons to the atom to make anions. So your halogens will have the most exothermic or most negative electron affinities because they're the ones that, with the addition of 1 electron, become stable. Does that make sense? All right. This one's an easy one. Which pair of elements is most likely to form an ionic bond? Ca and O. Always between a non-metal and a metal.
James would be disappointed.
All the rest of these are either polar or not polar. All right, we're going to do 7. 6 Karchi kind of did. We'll do 7. Which of the following compounds has the greatest lattice energy?
Small and large charge. Yep.
Anybody have an answer? Here, want a couple MGSs? Anything else? Anybody else have any other opinions? All right. So when we're dealing, you're probably going to get 2 questions on lattice energy tomorrow. One is going to be calculating lattice energy. One's going to look something like this. So, does anybody know what Coulomb's law is? This here, which is the attraction, the force of an attraction from 2 particles. That's what describes lattice energy. Lattice energy is the force that holds the particles together. As you can see here, force is directly proportional to charge and inversely proportional to radius. As you go down the periodic table, right, atomic radius gets larger. So that means force is going to get smaller. So the smallest ion there would be the magnesium ion. Therefore, it has the largest lattice energy because those force and lattice energy are inversely proportional. Now, if you had one where it was 1 plus and 1 minus, so something like KCl versus magnesium sulfide, you would still have magnesium sulfide would be the greater lattice energy because charge trumps radius. I know my section, you've heard that a couple times come out of my mouth, but if you have 2 plus charges, they're always going to have a higher lattice energy than the 1 plus charges, 1 plus, 1 minus. Make sense? What's up?
No matter if it's like farther down.
Yeah, because as you go further down, radius will still be just enough, just small enough to keep that greater. All right. Can we see this diagram? How about that? So we have a structure here for acetate on the top. Which of the following 4 structures is the best resonance structure for acetate? Why? But remember, all we do with resonance structures is move double bonds, double or triple bonds from one atom to another. As long as it's the same atom bonded to another atom. So we have the carbon bonded to 2 oxygens on the right side of the molecule. We can move that double bond from the top oxygen to the right oxygen, and that's the same structure. That's completely okay. So D is the correct answer for this one. All right, this one, another one I put my money on being on the test tomorrow, something like this. Using formal charges, which is the better Lewis structure, the one on the left or the one on the right? Show of hands, who thinks it's the left side? Who thinks it's the right side? All right. So, a couple things about formal charge. When you're drawing your Lewis structures, there are 2 things that you want to make sure you have exactly right so that you know you have the right structure. Number 1 is that you've used all the valence electrons. So if you have 26 valence electrons in your atom, make sure you've used all 26 in the structure. The second one is that there's 2 conditions on formal charge. The first one is your central atom. It should always be 0. The second one is that the sum of the formal charges for each element in your compound should equal the ion charge. So if it's a neutral atom, it should equal 0. If it's an ion, it should equal +1, +2, -1, -2, whatever the charge of the ion is. On the left, carbon, we'll start with the carbon, has 4 valence electrons. minus has no lone pairs, so it'll have 0, plus 1/2 times the number of bonding electrons. There's 8. 1/2 of 8 is 4. So that's 0. The nitrogen has 5 valence electrons, 2 lone pair electrons, 3 bonding groups, so 6 electrons. 1/2 of 6 is 3, plus 2 is 5, so that's 0. For the sulfur, it has 6 valence electrons, 6 lone pairs, plus 2 bonding electrons, so 1/2 of 2 is 1, so that's -1. For the right side, the carbon, 4 electrons, 0 lone pairs, 8 bonding electrons. For the nitrogen, 5 valence electrons, 6 lone pair, plus 2 bonding electrons. 1/2 of 2 is 1, 6 plus 1 is 7, 5 minus 7 is -2. For sulfur, we have 6 minus 2 plus 1/2 of 6, we have 1. So, while both of these check off both boxes, that the central atom is 0, and that the sum of the formal charges does equal the charge of the ion, it is the left side. Because you want to get as many formal charges down to 0 as you possibly can. All right? What's up? Yes, you do have that formula on the test. Yes.
Say both of them had 2 zeros.
At that point, it's 50-50. At that point, that's not going to happen. At that point, what has happened? So where the carbon, the sulfur would have -1 on one side, and nitrogen would have -1 on the other side?
So like nitrogen, like say nitrogen is sulfur.
Those are equal problems. However, they will give you one where one will definitely have more zeros than the other, or one will not have some of the formal charge will not equal the ion charge. You shouldn't have to deal with that tomorrow. I don't think they would try to throw that curveball at you. So number 10. Are the bond angles in BF3 greater than, less than, or equal to the bond angles in SO2? Draw yourself a Lewis structure. Draw it out.
No, it's like CO2. It's linear. Yeah. It's single bonds and you have lone pairs. If it's double bonds, you still have lone pairs.
Exactly, that's what I said.
So, any guesses here? Greater than, less than, or equal to? Raise your hand for greater than. Raise your hand for less than. Raise your hand for equal. All right, it's not equal. So, as I said earlier, remember, as you add lone pairs, the bond angles get smaller. So here, in BF3, we have 3 electron groups. So it's going to be trigonal planar. We have 0 lone pairs. So the bond angle is going to be 120 degrees. Again, we have 3 electron groups. So it will be trigonal planar in electron geometry. But we have 1 lone pair. So it becomes bent. Again, as you add lone pairs, bond angles decrease. So this is going to be less than 120. Therefore, the angles in BF3 are greater than the angles in SO2. Does that make sense? Any questions there? All right, 11. Determine the hybridization about carbon in H2CO. Draw yourself the Lewis structure.
There's a double bond. You don't have to know the outside.
Yeah, you do. Electron hybridization.
Or they're related.
Oh, I'm sorry. Yeah, you do need to know electron number, but
I don't feel like trying.
you don't really need to.
Yeah.
What you can do is a little cheat, which is all single bonds. sp3 and one double and sp2 two doubles. After that, just don't add these.
So, what do we think? SP2. Why is it SP2? 3 groups, right? 3 electron groups. Right around this carbon. 1, 2, and 3. All right. About halfway through this, so probably another 10 minutes. What is the molecular geometry of SEF4? This one's a tough one.
So it gets a D. Does it get 2 D orbitals?
How many electrons does SEF?
I think it's
6.
It is a square.
no. That's not a choice though. So it's a question.
What is it? Oh, it Oh, it's seesaw.
No, any answers? Any guesses? Seesaw.
Seesaw.
Any answers come in? I've heard all 4 answers. Go to the playground, it's a seesaw. Seesaw. Good job, Boston. Now remember, tables 10.1 and 10.3, if you do not know them by now, 10.1 would be the electron and molecular geometries, 10.3 is hybridization. Please, 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 please make sure you know those. Please. That is the test. If you know those 2 tables, you will do well on this test. So, seesaw, 5 total electron groups, 10.1, 10.3. Seesaw, 4 bonding groups, 1 lone pair. All right, sigma and pi bonds. Going back to H2CO, I just wrote it differently. How many sigma bonds? How many pi bonds?
3 sigma, 1 pi.
Nice. 3 sigma, 1 pi. Remember that a single bond is a sigma bond. A double bond is 1 sigma and 1 pi bond. And then a triple bond is 1 sigma and 2 pi bonds. Remember that. That's going to be important. You'll definitely get a question on sigma and pi bonds tomorrow. All you do is you count up the total number of bonds, right? So there's 1 sigma. A double bond is a sigma and a pi. That's a total of 3 sigma, 1 pi bond. Questions? All right. Straight from table 10.1. Which molecular geometry results in a central atom having 5 electron groups? 3 of those being bonding groups, while the other 2 are lone pairs. T-shaped. What if I had 6, 4 bonding, 2 are lone pair? Pointer, let's see.
T-shaped is
4 total, 2 bonding, 2 lone pair. I have 2 atoms. Linear. Linear is the only one for 2 atoms. What is the electron geometry for... What's the electron geometry for two bonding groups, 3 lone pairs? Trigonal bipyramidal. I asked for the electron geometry. Remember, electron geometry just counts the total number of groups. Molecular geometry goes to the specifics.
No, I was like trigonal.
All right. Another,
which
yeah, they call it species. I took the textbook I took it from calls it species. Which molecule has the smaller bond angle?
H3.
A couple people jump to conclusions here.
H3O and
So he's gonna draw something.
How many viewers do you have, Evan? Besides my good-for-nothing roommate.
7. Oh, that's mean. He can hear you, probably.
I have 2 roommates.
Okay, but like...
Again, both are tetrahedral electron geometry. H3O plus is 1 lone pair. H2O has 2 lone pairs. The more lone pairs, the smaller the bond angle. H2O.
That was...
So, 16A and 16B should be easy. Triple bonds have the greatest strength, right? What are the longest lengths? Single bonds, right? So remember, single bonds are the weakest, but the longest. Triple bonds are the strongest, but the shortest. Oh, damn.
No.
Yeah. If you go back to the original PowerPoint that's on Canvas, this is question 24, not 16. I pulled some. Don't worry about that. 17. Based on expected intermolecular forces, which of the following has the highest boiling point? Why? Yes. If you get a question tomorrow, and all 4 of them only have, let's say, dipole-dipole forces, like these 4 have, the tiebreaker is molecular weight. Right? So if you have all of them have dipole or all of them are polar, the tiebreaker is always molecular weight. So the heaviest molecules will have the largest intermolecular forces. That's what I'm getting to with this question. All right, 18. Which substance experience dipole-dipole forces? What's the characteristic for a molecule to have dipole-dipole forces? It's got to be polar. Which one's polar?
Could be CLC.
I'm gonna go with...
I think it's
NF.
CLC.
No, that's symmetrical and not polar.
Oh.
NF.
Yeah.
Yeah. Because it's like NH. Is NH3 polar? Yeah. Evan, is ammonia polar? NH3?
How many electrons does it have?
It's 1 lone pair.
If it's 1 lone pair...
All right, so we have an answer for 18. NF3, right? CCl4, we already know. You've probably done it 15 times. We know that's not polar. CS2 we did earlier. Linear, right? Non-polar. SO3 we did earlier as well, non-polar. We look at NF3. Right? The partial negative is all at the fluorines. We draw our vectors. These two cancel out. We're left with a vector down. That means we have a polar molecule. Did I say that's not polar? Trick question. Just do answers. SO3 is the same. Yes, SO3 is also polar. Although the book says it's only nitrogen. It's fine. It's still polar. What's up? Why are you dipole-dipole forces have to be from a polar molecule. Yes. Any questions so far on the conceptuals? All right. Why doesn't formaldehyde have a high boiling point even though it contains hydrogen and oxygen?
The hydrogen is not a hydrogen. Carbon and oxygen.
Every answer I've heard so far is right. Remember, for a hydrogen bonding to occur, hydrogen has to bond with either fluorine, oxygen, or nitrogen. The corniest way to remember that is it's not fun, it's FON. F-O-N, not F-U-N. So it's not bonded together.
Does this have
Right?
a
Look at the structure, right? Hydrogen is bonded to carbon, right? That's not FON. It's not FON. No, it's not FON. Okay, it's the corniest way to remember it. Remember, hydrogen bonding is the strongest intermolecular force we'll see. But remember, hydrogen's got to be bonded to fluorine, oxygen, or nitrogen. The only one, ion dipole is next semester. Ion dipole is all next semester. Ion dipole is the strongest, yes, intermolecular force, but we're not dealing with any ions being dissociated in water right now. That's the only time ion dipole occurs. Ions are dissociated in water. I have two samples of propane. One is at room temperature. One is heated to 500 Kelvin. Which is more viscous? Why? As you heat up the propane, first of all, one of them isn't liquid anymore. And if it stayed liquid, as you heat the molecules up, increase the intermolecular forces. I have an example of propane and water. Which one's more viscous, propane or water? Here's both answers. Raise your hand for water. Raise your hand for propane.
Hey, how do you tell what's more viscous?
Intermolecular forces.
Do we need to know?
Propane, it is FON.
Water has hydrogen bonds, so it's more viscous.
Water is FON. What am I saying? So much fun. So much fun. Propane, its strongest intermolecular force is London dispersion forces. Water has hydrogen bonding. The stronger the intermolecular force, the more viscous it becomes. Question 21. As temperature increases, what happens to vapor pressure? Yes, same reason. You heat up the molecules, intermolecular forces decrease, therefore vapor pressure. All right, last slide. What? Which one? I can't hear you. 21. As you heat something up, the intermolecular forces decrease. As the intermolecular forces decrease, vapor pressure decreases. Vapor pressure is caused by intermolecular forces.
Same thing, all the same.
All right. 4 questions, and you'll be out of here an hour and 30 minutes earlier than you were yesterday. Yeah. 22. At point E, what process is happening? Roll. Melting, or what's that fancy word you're using tomorrow?
I'm glad I didn't go.
23. Directly below point F. I John was a really bad voice crack. Directly below point F. What state is that substance in? Gas, yes. What's the technical term for point D? Above point D, above point D, what type of state of matter is it? Critical fluid. And question 25. What point is vaporization occurring? Well done. Ladies and gentlemen, best of luck tomorrow. I'll get down here for 5 minutes. Have a good night. Don't study too hard.
Yeah, me too.
I'm not studying. I'll be studying.